Hello my friends and welcome back to the Today Machine channel. Around 44 million tons of steel are produced in Germany each year. An important raw material for production is scrap steel. The stainless steel works in Witten, Germany, are considered world leaders in the field of high alloy specialty steels. In a massive electric arc furnace, the scrap is melted and processed into steel. About every 90 minutes, the steelworkers in Witten power up the gigantic furnace, and the inferno begins. Working at this hell furnace is a sweaty, grueling job. The monster processes about 75 tons per hour, with temperatures in its belly exceeding 1,700 degrees Celsius. After the tapping, the furnace door must be cleaned of the still glowing slag. Even for the toughest workers, it's too hot, so a machine takes over this task. Every year, the Witten Steelworks process around 500,000 tons of scrap steel into high alloy specialty steel for the automotive industry, aerospace, medical technology, and offshore wind industry. And who knows, if the steel products ever reach the end of their life, they might end up back here, in the belly of the hell furnace, at 1,700 degrees Celsius. The journey continues. The still glowing steel blocks are now hardened in the rolling mill. With a joystick, operator Stefan Seaweed controls two counter-rotating rollers that maneuver the ton-heavy block back and forth as if it were a toy. These slabs are heated in a reheating furnace to temperatures around 1,100 to 1,300 degrees Celsius, 2,000 - 2,400 degrees Fahrenheit, to soften the material, making it malleable for rolling. The reheating process is essential to achieving the right temperature for efficient shaping and to avoid fracturing the metal during deformation. Once the steel slabs reach the required temperature, they are transported via conveyors to the roughing stands of the hot rolling mill. In the roughing mill, the slabs undergo multiple passes through large rollers that gradually reduce the slab's thickness. These rollers are powerful, exerting tons of pressure on the heated steel, which compresses the material. This initial phase may reduce the thickness from hundreds of millimeters to just a fraction of that. The semi-finished product then moves on to the finishing mill for further rolling. In this stage, more precise adjustments to the thickness are made to meet exact specifications. This is achieved through successive passes through rollers, further elongating the slab and improving its surface quality. The rolling mills are often equipped with sophisticated control systems that monitor and adjust parameters such as speed, temperature, and pressure to maintain product uniformity. After final rolling, the steel is rapidly cooled, usually through water quenching or air cooling, depending on the desired mechanical properties of the final product. The rolled steel is then coiled or cut into plates or sheets as per requirements. Bremen Machinery introduced a new plate rolling machine with remarkable capabilities. This three-roll machine, manufactured by the Heisler Company in Switzerland, took approximately a year and a half to build. Weighing in at an impressive 320 tons, the machine required a special foundation to be installed before it could be put into operation. The plate rolling process starts with a flat sheet that has a small overlength on both sides. This extra length is essential for creating precise edge seams. The process of adding these edges must be carried out with high precision to ensure a perfectly round final result. Once the edges are added, the plate is carefully marked and prepared for the cutting process. To facilitate accurate cutting, the plate is preheated, and as the excess length is cut away, the weld edges are also created. The sheet, now cut to size and with its weld edges, is ready for rolling. Once rolled, the resulting shell will have an external diameter of 2076 millimeters. This press brake is one of the heaviest in Europe, boasting a bending capacity of 3,000 tons across 8,000 millimeters, with a per meter bending force of 800 tons. This powerful machine is demonstrated by bending a 60 millimeters thick, 7.2 meter long stainless steel plate into the required radius. The film showcases the impressive feat of rolling a 43-ton steel plate, which is 150 millimeters thick and 2,230 millimeters wide, into a diameter of 5,000 millimeters. After the rolling process, the seams of the rolled shell are welded together using a highly efficient welding method, where two filler wires are used simultaneously to speed up the process. The welding is covered with a powder layer, and any excess powder is recycled for future use. This is a vital piece of equipment used in the assembly of cylindrical structures, such as columns, wind power plant towers, and offshore structure supports. It is designed to securely position and align shell segments for precise assembly. The stand includes roller blocks whose distance can be adjusted using hydraulic cylinders. This hydraulic system allows for smooth and accurate positioning of the shells. The process begins by adjusting the roller blocks to fit the shell. The shell is then leveled, either manually or automatically, to ensure proper alignment for welding. Once the shell is positioned, the welding process is initiated. This involves initial welding to join the shells, followed by additional welding passes to strengthen the joint. After welding is completed, the assembled shell is transported upward to make room for the next workpiece. The cycle is repeated, with each new shell being positioned, leveled, welded, and moved, ensuring continuous assembly of the cylindrical structure. The hydraulic controls and precise movement capabilities of the stand are essential for maintaining accuracy and efficiency throughout the assembly process. In steel production, precision is critical to ensure that every transition piece meets stringent quality standards. Transition pieces, commonly used in offshore wind farms to connect foundations and towers, are crafted with exceptional accuracy and attention to detail. The process begins with the steel fabrication stage, where each component is carefully cut, shaped, and welded. The steel undergoes rigorous quality checks to guarantee that it meets the required specifications for strength and durability. Special attention is paid to the accuracy of each item during this phase, as deviations can impact the overall integrity of the transition piece. Once the steel components are assembled, the transition piece is prepared for coating. A multi-layer special coating system is applied following strict procedures. This coating serves to protect the steel from harsh environmental conditions, such as saltwater corrosion and weathering, ensuring long-lasting performance. After the coating is applied, the transition piece enters the assembly phase, where the platform is welded and outfitted with essential components. These include railings, lights, cables, and gratings. All installations are carried out with precision to ensure safety and functionality. This dishing press machine is designed to shape metal sheets into a concave or convex form, commonly used for manufacturing vessel heads, tanks, and other rounded structures. The process of dishing involves applying force to a flat metal sheet, typically steel or aluminum, using either hydraulic, mechanical, or CNC-controlled systems. Hydraulic dishing presses utilize fluid pressure to gradually form the desired shape, while mechanical presses apply force through mechanical action. CNC dishing presses allow for precise and automated shaping with computer control. The choice of machine depends on the material, size, and shape of the final product. Dishing presses are widely used in industries such as petrochemical, automotive, food and beverage, and shipbuilding for creating parts like boilers, storage vessels, and pressure tanks. These machines offer high precision, efficiency, and customization, making them essential for large-scale manufacturing. The flanging machine is an industrial tool used for shaping and bending metal edges to form flanges on workpieces. Flanging strengthens the edges of metal parts and prepares them for joining with other components, offering both functional and aesthetic benefits. Flanging can be performed on various metals, including steel, stainless steel, and aluminum, making it versatile for a range of applications. There are different types of flanging machines, such as tube and pipe flanging machines, which create flanges on cylindrical workpieces like pipes, and sheet metal flanging machines, which form flanges on flat metal sheets. Radial flanging machines are another common type, which are used to create flanges around the radial beam of a workpiece. Flanging machines are critical in industries like automotive, aerospace, HVAC, and oil and gas. In the automotive sector, flanging is used for producing body parts and panels, while in aerospace, it's essential for aircraft component manufacturing. Flanging machines are also extensively employed in duct fabrication for HVAC systems, as well as in the construction and railway industries for equipment manufacturing. Household appliance manufacturing also relies on flanging for creating durable, aesthetically pleasing components. The hot forming method offers several advantages over other forming methods, particularly when producing a Hemi head with a diameter of 125 millimeters. These benefits make hot forming ideal for applications that require precise and high-strength components like pressure vessels, gas cylinders, and tank heads. Hot forming involves heating the metal to a high temperature, which significantly increases its malleability. This makes it easier to shape complex geometries, such as the hemispherical form of a hemi-head, without the risk of cracking or excessive thinning. In contrast, cold forming or room temperature methods could lead to material failure due to limited ductility and formability at lower temperatures. Since the material is more pliable when hot, the hot forming process allows for better control over the final shape and dimensions. This is especially important for achieving the correct curvature and uniform thickness of the 125 mm hemi-head. Cold forming processes may struggle to maintain consistent wall thickness, leading to material weakness in certain areas. Hot forming reduces residual stresses in the material, which are commonly encountered in cold forming processes. By heating the metal, internal stresses are relieved during the forming process, which enhances the overall mechanical properties and integrity of the hemi-head. This makes the final product more reliable under high pressure or high temperature conditions. Some materials, such as high-strength steels or alloys, are difficult to form at room temperature due to their hardness and strength. Hot forming overcomes this limitation by making these materials more pliable, enabling the production of a hemi-head that retains high strength after cooling. Other methods, such as cold forming or spinning, might require excessive force, leading to increased tool wear or product defects. Once the steel plates are selected, the manufacturing process begins with cutting the plates to the required dimensions. This is typically done using CNC plasma or laser cutting machines for precise, smooth edges. After cutting, the plates are bent into a cylindrical shape using large hydraulic plate rolling machines. The bending process must be precise, as any deviation can cause issues during the welding process or lead to a defective pressure vessel. Once the plates are shaped, the next step is welding the longitudinal seam to form the cylindrical body of the pressure vessel. Specialized welding techniques like submerged arc welding, SAW, or gas metal arc welding, GMAW, are often used for these critical joints to ensure the strength and integrity of the welds. After this, the body is inspected for any defects or imperfections that could compromise the vessel's performance. Simultaneously, the heads of the vessel, which are typically hemispherical, elliptical, or dished, are fabricated. These are either pressed from steel plates or formed by spinning. The head fabrication process also involves cutting the steel to the appropriate shape and welding any sections as needed. If multiple pieces are used to form the head, each segment is carefully welded together, ensuring full penetration welds that can withstand pressure. With both the body and the head sections prepared, they are assembled and welded together. This process involves welding the circumferential seam where the body meets the heads at either end. Again, high-strength welding techniques are employed to ensure that the entire structure is sealed and secure. Post-welding, non-destructive testing, NDT, methods, such as ultrasonic testing or radiographic testing, are often used to check for any internal defects in the welds. Once the entire vessel is assembled, it undergoes pressure testing to ensure its integrity under operational conditions. This is usually done by hydrostatic testing, where the vessel is filled with water and pressurized to a level above its intended operating pressure. This test ensures that the vessel can safely hold pressure without any leaks or structural failures, making it ready for use in pressure filtration systems. Bremen Machinery's creation of the Chela crane for the offshore industry is a remarkable example of precision engineering and the utilization of modern technology to meet industry demands. This innovative crane, named after the claw-like movement of a crab's pincers, was designed to streamline construction times and enhance safety in the often hazardous offshore environments. The company's advanced manufacturing facilities and expert team played a pivotal role in the successful development of this crane. Collaborative design and engineering. The Chela crane was produced in close collaboration between the company and its client in the offshore sector. Offshore projects demand high-performance equipment capable of withstanding harsh marine conditions while adhering to strict safety standards. In this project, the engineers, project managers, and mechanics at Bremen worked hand in hand from the initial design phase through to the final product, ensuring that the crane met the rigorous NORSOK standards, which are essential in the oil and gas industry for ensuring operational safety and structural integrity. One of the defining features of the Chela crane is its ability to emulate the natural movement of a crab's claw, which provides enhanced maneuverability and precision in lifting and positioning operations. This unique feature significantly reduces construction times by allowing the crane to operate in confined and complex environments with greater efficiency compared to traditional cranes. Fabrication and corrosion protection. Fabrication of the Chela crane took place in Bremen's Genehmigungen facility, where modern workshops and specialized equipment ensured the steel components were produced with high precision. The welding department, known for its state-of-the-art welding machines and highly trained welders, was responsible for the critical welding processes. The company's commitment to quality was evident in the traceability of every weld, with each one being assigned a unique identification number to ensure thorough quality control throughout production. The corrosion protection of the Chela crane, crucial for offshore equipment exposed to corrosive marine environments, was also carried out in Genehmigungen. Bremen's blasting and spraying workshop, equipped with offshore coating capabilities, provided a comprehensive corrosion protection solution, ensuring the crane could withstand the harsh conditions it would encounter offshore. Assembly, testing, and installation. Once the components were fabricated and coated, the assembly of the Chela crane took place at Bremen's IJmuiden facility. This facility, strategically located near the sea with ample space and crane capacity, was ideal for assembling the massive structure during the winter months. The assembly process included the crane's structural integration as well as the installation of its hydraulic and mechanical systems, a testament to Bremen's ability to handle complex offshore machinery. The functional acceptance test, FAT, and load test were also conducted at IJmuiden, ensuring that the crane met all performance and safety requirements before being delivered to the client. The final step in the production process involved third-party installation and programming of the crane's electronics, completing the fully integrated system ready for offshore deployment. Modern machines plays a crucial role in steel fabrication, enabling companies like Bremen Machinery to meet the growing demands of high-quality, complex projects in industries such as offshore oil and gas, wind energy, and infrastructure. At here, state-of-the-art equipment is at the core of their operations, ensuring precision, efficiency, and the ability to tackle large-scale steel fabrication tasks. Advanced welding technologies. High-quality welding is essential in steel fabrication, particularly for projects that require the structural integrity and durability to withstand extreme conditions, such as those in offshore environments. Bremen Machinery's welding department is equipped with some of the most modern welding machines available, and its team of skilled welders is trained in various welding processes, including submerged arc welding, SAW, MIG, MAG, and hot wire TIG cladding. The precision offered by these modern welding technologies allows for the fabrication of steel components that meet the strict quality and safety standards required by clients in industries like offshore oil and gas. Additionally, Bremen's approach to welding includes thorough quality assurance measures. Each weld is meticulously tracked and documented, ensuring full traceability throughout the production process, which is critical for both quality control and compliance with industry standards. CNC controlled machines for precision and efficiency. One of the cornerstones of steel fabrication process is the use of CNC controlled machines for turning, milling, and boring operations. These machines are essential in achieving the level of precision required for manufacturing steel components used in critical applications, such as offshore cranes, wind turbines, and industrial machinery. CNC technology allows for the automated and highly accurate production of steel parts, reducing the margin for error and significantly speeding up production times. The ability to program these machines for specific tasks ensures that Bremen's operators can produce complex geometries and maintain tight tolerances, even on large-scale projects. For example, in the manufacturing of components for the Chala crane, CNC-controlled machining ensured the precise shaping of steel parts that would later be assembled into the crane's complex structure. Corrosion protection and surface treatment. In addition to machining and welding, corrosion protection is a vital aspect of steel fabrication, especially for products destined for offshore or marine environments. The dedicated blasting and spraying workshop provides a comprehensive solution for corrosion protection, ensuring that steel components are coated with durable, protective layers to resist the harsh conditions of seawater, humidity, and temperature fluctuations. The availability of in-house corrosion protection services is a significant advantage for the company, as it allows the company to control the entire fabrication process, from raw steel to the final coated product. This not only ensures consistency in quality but also reduces lead times, making the company more responsive to client needs. Heavy lifting and assembly facilities. The facilities are equipped with cranes capable of lifting up to 320 tons, enabling the company to fabricate and assemble massive steel components. This capability is particularly important for projects involving large offshore structures, such as cranes, grabs, and other lifting equipment. The ability to fully assemble these components in-house, before transporting them to their final destination, ensures that any issues can be identified and addressed early in the process, reducing the risk of costly delays during installation. Bremen's strategic location, with direct access to waterways and proximity to major ports, also facilitates the efficient transport of large steel structures to clients around the world.